And away we go. So we'll do the lecture that we started yesterday, which means, well, we'll be doing some coding. But what really means is that we've already gone over these learning outcomes. I'll just give a quick overview, and then I'm going to have the opportunity for more questions about assignment 1, just in case new stuff came up just yesterday. But it's worth repeating. We're going to talk about getting line-based input using fgets and how that differs from other input methods we've used before, like getC. And describe contents of in-application memory management. I think that's the stuff I'm going to skip. It's very useful for understanding the why behind a lot of things in this course, and it will be on the test. But like I mentioned earlier, some stuff from the next lecture is more important and applicable to the second question of the assignment specifically. So we're going to skip that for now. And then write code that takes advantage of its environment through the redirecting of standard input and output for file I/O. That's what we're doing today. You'll see at the end, we don't actually get to that learning outcome in the lecture. So again, we're skipping. But before we get into that question 2 stuff, are there any new questions about assignment 1 since last time? Looks like not, but I'll give like 20-ish more seconds in case anyone needs time to think about how to formulate the question. Yes?
I don't know if you'll be able to answer this.
Bring it.
Because we're trying to replicate like the exact same results from the Java file, right?
Yeah.
And one of the test cases has like a string that like in the middle of it has the end of a character thing.
Yeah.
And I don't even know what my question really is. It's just
The answer is yes. That test case is nasty. It was added specifically to confuse people. Your program must still act identically to the Java program, which involves reading that entire string beyond the end of string character. So basically, you can't use strlen or sternlen, but you could still use what else you know about strings and arrays to ignore that character. Slightly more detailed hint, there is a way to communicate the length of a string to another function other than using strlen that should be in one of the examples. Any other questions? Yeah?
So we cannot use strlen?
It's not that like I'm banning strlen. There's nothing wrong with using it. But in order to cover that nasty test case that has that end of string character in the middle, strlen won't work, and you'll have to find some other solution. Yes?
So the test case with the end character, we're supposed to test it.
Yeah, so all the test cases in the Java program should be in the C program.
But there's a comment there that says we shouldn't care about it.
In the Java program?
Yeah.
Let me check that. They're maybe thinking about the one that's supposed to fail, but I'll check it just to make sure I know what I'm talking about before answering. Ooh. Oh, are you talking about the wording of we shouldn't care? That means in this case, you still have to include and respect the test case. What it means by shouldn't care is that it should skip the null byte and process the entire string as given. Give like 10 seconds more for, yes? Are you saying that, like, that we shouldn't add calls to C's assert function? Okay. Let me just read that. You don't have to worry about that. What that comment is saying is that the return value must be true or false. It can't take on some mysterious third value. But the type system just guarantees that it'll be true or false because it's a Boolean. In C, we use just any numerical values in place of true or false. So because of how it interprets 0 as false and anything else as true, we basically have the same guarantee. So the same idea applies in the C program, and you don't need to add any extra assertions to guarantee this. If we were coding in Python, perhaps you would have to assert that your function actually returns a bool and not an int or a float or a string or whatever. I don't like Python. But luckily, C has a static, i.e. sane, typing system, so we're good. Going to give another 10 or 15 seconds or so for questions. Cool. Let's move on to some of tomorrow's content. Tomorrow, you should be able to do this stuff specifically. The second question revolves around taking advantage of your environment and redirecting standard input and output. So today, I'm going to talk quite a bit more about what std in and std out are, and explain how to use those data files that I uploaded into the assignment folder. So don't have to worry about this yet. Boom. Command line programs have these two streams of data, which are sort of like files, but never ending. There's no explicit end to the user's keyboard input, for example. So you have standard input and standard output. Standard input is, well, it represents anywhere where data comes from. Most often, it's the user's keyboard input. Whenever you've typed stuff into a program, you would be using standard input. But you can redirect things into it, which gives your programs quite a bit of versatility, which we'll finally see soon. So you could redirect files into it. You could redirect the output of other programs to it. Say you have a program that outputs some text and another program that is a spell checker, maybe. You could redirect standard input to easily bring the output of one program into the input of another. Even other devices, so in distributed computing, this or interprocess communication, this can take the form of an internet connection and you receive messages from another device. That's another thing you could redirect through standard input. And you can use standard input in Java using system.in, which is similar to the stdin file pointer we used yesterday. Standard output is where data goes to. Usually it's the text on your screen. You printf, and then the text shows up on screen. Easy. But you could also write to files, make it the input of other programs, or even do stuff like print, like actually print on legit paper. And of course, send stuff to other devices. This is the real important stuff. You can change the source or destination of I/O on the command line using the redirection operators. The little lesson sign, it'll be much clearer when I give an example, but it'll appear to be pointing into the program that you're running, and that's the input redirection. And likewise, the greater than sign looks like it's pointing out of the command you're running and is the output redirection operator. I'm going to do a live demo on the command line, basically show you how question 2 of the assignment should work. But this is a nice little canned example. So this program is called my program. We have no idea what it does, but let's say it has calls to getC or fgets, and thus gets keyboard input. This will redirect standard I/O so that whatever is stored in file.txt is sent to my program, and my program thinks that the contents of file.txt is keyboard input. So we basically get file reading for free, which you may or may not understand the gravity of. Reading files is very obtuse a lot of the time, so this is a pretty awesome tool to have. So the same thing applies to standard output. My printing program has calls to printf or some similar function, and it redirects output into the output.txt file. I use this all the time when a program outputs a lot of data, like logs, for instance, and I want to save those logs to see later. So rather than having it just dump into my terminal and then select all of it, copy and paste it into a file, you could just make it go straight into a file. Yeah, like that. And this won't be in the assignment, but will definitely be useful later. You can use the third redirection operator, the pipe, to have one program's output be the input of another. You could technically also do this by having the first program redirect its output to a file, and then have the second program redirect its input to that file. But this is a much more elegant way of doing that. So whatever my printing program prints will be the input, the keyboard input for my program. Then I think that's the gist of input and output streams. Sure is. Now I'll do an example of how to use these. So I'm in my folder for the first assignment, and I'm going to redirect some input. So first, I'm just going to run perfectly balanced input, the file for the second question, without any fancy redirection. Weird. Okay. You may or may not need to know what I just did for troubleshooting. This is sort of advanced Unix that you don't need to know for the course, but as you just saw, might need to know for when things just don't work. What I just did was I added the execute permission to perfectly balanced input, which gives your current user permission to execute the file. Unix has more file permissions like that. You could configure whether certain users are able to read, write, or execute the files. I don't know why my own executable wasn't marked as executable, but I was able to fix it by using +X, add the executable permission. Oh, come on. Oh, I'm being blocked by the whole OS? I know this will work if I SCP it into Aviary, but I'm going to keep trying to get it working locally. And in the process, show you another useful trick. The open command takes a file and opens it in its default program on the GUI. So if you had a HTML file, using the open command on it would open it in your web browser. Now I'm passing the current folder, represented by dot, into open, and you know what program opens folders? The file manager. So in my case, it opens Finder. On Linux, it'll open up whatever file manager you have configured. And I'm just going to try to use a workaround for Apple thinking that this might be a virus because it doesn't know exactly who it came from. Okay, seems to be working now. For any Mac users that run into this issue, if it blocks an executable, it won't work when double-clicking it, but then right-clicking and then selecting open will give you a slightly different prompt. Instead of, "Nuh-uh, you're not allowed to open this," it says, "Are you sure you want to open this?" And then it lets you open it. So I think we're finally ready to match some brackets. Yeah, not sure what's going on here either. I'm just going to give up and go to Aviary. Oh, right. Oh, it must have been dismissing all of my input because it's invalid. Nice. Also nice. thank you guys very much. So, I just used my keyboard. Yippee! This is perfectly balanced input using standard input, as expected. So, this is cool, but if you have, oh yeah, question?
If our assignment works like this, we can submit it, right?
Yeah.
So there's some involved in the TXT file. So if it works like this, it's fine.
Well, the answer is probably yes, but you should definitely test it with the TXT files. Sorry, you got to learn about input redirection. You got to make it work with TXT files using the input redirection operators that I'm about to demonstrate. And because input redirection is so cool, if it works like this, it probably already works with text files. You just got to test it. So yeah, say hypothetically, I have a bunch of test cases, and I don't want to just write them all by hand every time. I could instead store them on a file and redirect them. Crazy. So I pressed Control-C to exit this program, and I'm going to show off the first data file. Yeah. So this first file just has a bunch of strings that have balanced brackets and should have a result of having balanced brackets. Nothing too exciting. I'm going to do this again with cat so it shows up on the terminal. That way we can refer to it if needed. So / perfectly balanced input. Woohoo! Autocorrect is predicting exactly what I want to do. We're going to use input redirection. The lesson sign looks like it's pointing towards the program. And then the path to the file that you're using for standard input. And then should just work. Ta-da! And you can do the exact same for data 2 through data 5. I wish I could show you the C code, but I can't. The code just uses good old fgets. Nothing different from regular program that just uses a regular keyboard input. But with the input redirection operators, we're able to just make it use text. And just to toy around, I'll show off a pipe. We could pipe the output of this program into less. And then this looks a little messed up because the characters used to change the text color in the output, less doesn't really know how to interpret them. And also this isn't even a very useful example because there's so little output and you don't really have a need to print it out anywhere but the terminal. But this just goes to demonstrate the limitless potential of being able to just pass one program's output to another's input. And for completion's sake, let's try it with a file too. Sampleoutput.txt doesn't exist. It should be able to just make a new file. And then nothing seemed to happen, but the program executed just fine. this warning is because of those characters that modify the text color. We're going to say, yeah. That didn't show up on the output, but I pressed Y for yes in response to the see it anyway prompt. And in this case, we just saved the output of our file, or output of our program to a file that we can then view later without modifying our program at all. So that's what I wanted you to know about input redirection. You now have, I guess, a day extra to work on question 2. Are there any questions about input redirection? Oh, sorry. Yes?
So fgets reads user input and file.
Yeah, like it reads standard input, which can be user keyboard input or file input or a few other things. Okay. Oh, yeah.
You know how when we're trying to process strings, we use char arrays, and we use pointers?
Are you asking if I used pointers in my solution to assignment 1?
No, I'm just saying in general, can we use pointers?
Oh, okay. Char arrays and pointers to char are more or less equivalent, but I think in general, people use pointers to reflect that they're sort of worked with differently than arrays. The distinction doesn't matter too much, though. If your functions take char arrays as parameters, that functionally isn't any different than if they take char pointers as parameters. Okay, looks like there are no more questions, so let's get on with today's lecture as usual. So last time we did line-based input with fgets, and it didn't really work that well. And I assured you that it was scripted and the solutions to our problems would come in the next lecture. Now we're going to see them. Yeah. And this is also going to involve lots of drawings. So one of the issues is that we pressed enter to end the current input, but then it just included that new line in our, or in the char array, or the string. So we got to fix that. So fgets reads a file or a file-like object, like a stream, until it sees a new line, which is then written to the buffer. So let's show what gets written to name over time. And of course, this won't show up for anyone just watching the lecture recording after the fact, but I will post these drawings separately, like as PDF files to the course website. Also, I'm going to be using pencil this time so I can erase stuff. If the pencil markings turn out to be too light for anyone viewing, just let me know and I'll switch back to pen. So Memory, as we know, is just an endless row of slots. Where each slot contains it contains one variable, whether it be an int or a char or whatever. Real memory uses bits separated into, or grouped into bytes and further grouped into the device's word size. But we don't need to worry about that now. You will worry about it in operating systems, and you'll worry a lot about it. So name is a string, which is actually an array, which is actually a memory location. And let's say it just points to the beginning of our tape. So I enter my name, and it goes Z, O, E, Y, new line, end of string character. So to remove that new line, we're going to just add another end of string character. This one will turn kind of useless, but it's okay. Once the end of string character is seen, we don't need to worry about the contents of the array beyond that point. So let's journey back into Aviary. Go into the Comp 2160 folder. And I think I called this input example. Yeah. So how are we going to get that specific memory location? Well, oh yeah?
Is there a preference versus using the define at the top of constants versus the constant?
Yeah, you should generally use define. I was trying to use const to demonstrate why it won't work in general, but this turned out to be a situation in which it did work. Basically, const is not necessarily a constant, but a read-only variable that can be set once. And that just doesn't sit well with how C defines arrays. So in order to define a constant that will work every time for defining the length of an array, use hashtag define. So the end of string character gives us the nice property of being able to figure out the length of the string using strlen. And I'm going to write the indices of each character to aid in explaining exactly what arithmetic we're using. We're going to use strlen on the character and get a length of 1, 2, 3, 4, 5, because it includes the new line character as a character. So, as we know from grade 1, 5 minus 1 equals 4. So we're going to use strlen minus 1 as the index, and then overwrite this with the end of string character. which will make our string 4 characters long and without a new line as intended. The very small name length might give us trouble, like it being set to 5. If it does, we'll change it, but we're just going to go onwards, hoping that it'll give us enough space to work with for now. So we're going to set a specific character, which is the exact same process as setting a specific element of an array. Name at strlen of name -1 equals the end of string character. Easy. Colon WQ to write a command that saves and quits. Yep, forgot to include string.h. Let's fix that. I use lowercase o to insert on a new line, and I'll just do the thing. And then the up key to access previous commands. Okay, so the buffer indeed didn't give us enough space. That's another issue that will be discussed in the slides. But for now, also, I use Control-C instead of D to stop because that inserts a new line for my next command and avoids that weird output we saw last class. Finally, it works. And our other issue is that if our input was too long for the buffer, it would start to look kind of weird and repeatedly give the hello message. Like that. Before I get to that, I think I want to explain why 5 characters wasn't enough to store the name. I'll just leave this all in suspense and give the most anticlimactic explanation for it ever, because it turns out this is just a known issue and you don't have to worry about it. But for now, let's just talk about why an array length of 5 wasn't enough. Actually, I'm going to switch right back to the laptop. The issue here with an array of length 5, which we set to 10 to fix a problem, was not in the declaration or definition of the array, but in the fgets call. It takes name length it takes the length of the string it's reading as a parameter, and then reads that many characters minus 1. The reason it does that many characters minus 1 is to give enough space for the null byte. So I'm just going to erase these. Pretend that the tape really is just our char array of length 5. Aha, just prevented an off by 1 error. So we typed ZOEY, enter. And that's not enough space for the end of string character. But we told fgets that we only have 5 bytes, or in this model, memory slots, in which to store the string. So it overwrites the last character with the end of string character all by itself. And then actually, if we didn't make that change that was necessary to handle strings in general, this would have output just fine. But our solution to how strings that didn't exactly fit into 4 characters had that awkward new line was to make the string 1 character shorter by adding an end of string character right before the end of string character. So it overwrote that last Y with an end of string character. And that is why it just called me ZOE. We accidentally deleted the Y. And actually, people think my name is that. I have to correct them Zoe with a Y. It's kind of annoying. Maybe I should have chosen ZOE. Whatever. Now, where were we? I think we were talking about why this E happens. And I'm going to give a logical but somewhat useless explanation for it. Oh yeah, here's our solution. So why does this happen? It's because fgets only reads the specified number of characters. We gave it 10 characters in which to store the input string. So it read, this should be 10 characters. I don't feel like counting. Actually 9, because the last one will be left overwritten by the end of string character. Wait, that really doesn't look like 10. Hold on. Yeah, it reads 14 characters. Well, the exact length of the buffer doesn't matter for this explanation. It reads a specified number of characters. And then once it's read the specified number of characters, the code goes on, and then we eventually get to the next fgets call, in which it sees that there's still a bunch of E's in standard input. This is equivalent to if your file has multiple lines, then fgets will stop after reading the first line, and then successive calls to it will just keep reading lines until the file stops. So that's why it gets more E's until it fills up the buffer, and yet more E's there, and then eventually stops. So we already did some drawing and solution. I don't know. For now, this is just something frustrating that we'll have to work around for keyboard input. For file input, it'll be much more elegant. We just need to give it a buffer size that's longer than any line of the program, or any line of the text file should be. I believe the sample solution for question 2 of the assignment uses a buffer size of 100. So every line of that file should fit, well, it will fit because we made the file, in 100 characters or less. And for now, until you learn better ways of getting input, this is the best we can do. And actually, I think I'll do a quick drawing because the mechanics of this are slightly different from the earlier example. This should be getting a bit predictable, I hope. So we type and then it puts as many characters as it can in the buffer. That code used a buffer of size 10 or 15. This uses a buffer of size 5. The exact size doesn't matter. What does matter is that fgets has processed this character, that character, that character, and that character, and still has a bunch of E's left. So on the next time it gets called, it just overwrites the string with E's. This shouldn't be super mind-blowing. The previous example of moving around null bytes and stuff should be much more exciting. For here, it's just worth mentioning that it reuses memory. Yippee. So, going to be making more drawings. And those drawings, we're going to look at how the OS manages memory, and the terms stack and heap will finally gain some meaning. Yeah, I'll show this slide and then it'll serve as a little introduction to what I'm drawing. So memory in a program is divided into 3 parts: code, heap, and stack. The code section is the executable code of your program. This is elaborated on in Comp 2280, but basically code and data are the exact same thing, and your computer executes programs just by reading data that you told it was executable, perhaps by typing chmod +x, or right-clicking and pressing OK or open on a file. But other than that, there's nothing separating it from everything else in memory. And that was actually a pretty mind-blowing idea back in the day. The idea of a general-purpose computer wasn't an intuitive one, I guess. So the next section is, actually I'm going to skip to the stack and get to the heap after. Another section that we're looking at is the stack. This contains all the stack frames of your program, for which every function you call has its own stack frame. A function's stack frame includes the function's code and all of its local variables. Probably shouldn't be explaining it in this much depth. I should just get on to drawing a picture. But I'll finish up the overview by talking about the heap, which is which holds the rest of the program's data. and it does so in an unstructured way. While the stack is pretty precisely organized, with memory separated by function, the heap is just a pile of stuff. And the stack has convenient memory management features where the memory required by a function is freed when you return from a function. The heap you have to manage yourself. So, program's memory layout might look something like this. I'm drawing it as a vertical rectangle this time. But you could imagine this as being like this tape, except extremely long and separated into sections. And it starts at address 0, contains the code section. So all of your executable stuff, like, I don't know, your entry point. That's all stored here. You could think of it as being like the text of your program that you put in a text editor. But of course, it has to be compiled and stuff first, and we'll talk about that later. Whatever. I'm going to skip to the stack again and draw it on the bottom here. And this is given a specific section of memory to work with, and stack frames are added to the stack as you call functions. And the rest is the heap, which we don't have to worry about right now, but you will worry quite a bit about later. Woohoo! So we'll look at what a stack frame looks like. I'm referencing a drawing of this stack frame for a main function. No chance of memorizing this. You all have no chance of memorizing this. You don't have to, but you should be able to explain what parts of memory there are and what a stack frame is on a test or something. So one stack frame might look like a big old stack of stuff where you might have the arguments passed into a program as the very first things on the stack. And then space for local variables. I'm just going to look at a program and see if I could reference some example that we've done earlier in the course and actually, use the variables in that function in the drawing. Might make it a bit more applicable. Yeah, so I'm going to use our input program, which has two local variables, the integer name length and the char array name. And it also has a return value. I'm also going to make this less wide because drawing all those lines can get painful. So this is a simplified model, of course. The operating system may or may not store stack frames in exactly this way, but it will do something similar to this. So it might have a space for the constant int name length. And then after that, you might have name, indices 0, 1, 2, 3, and 4. We're, of course, using that five-element buffer for this example to avoid me having to draw all those numbers. And then there's some more interesting stuff that's stored on a stack frame, such as the return address. For a main function, the return address is some sort of pointer to operating system code that describes what to do when a process exits. But for any function that you call, the return address points somewhere in the code section to show where to return after the function returns. And then it would also have its return value. And then also pointers to, I want to say objects, pointers to things that are often used, such as stdin. And stdout. You can copy that down if you want, but if you're trying to sear that into your brain for a test, you're kind of missing the point. The point that I'm really making is that it stacks stuff on top of each other. Woohoo! And that all these things are next to each other in memory. We've been talking about out-of-bounds array accesses a lot in the course, and this kind of illustrates how dangerous that could be. If an attacker is using, or if our program has a buffer overflow exploit, which is where the input string is longer than the buffer or array or whatever that we use to store it, and it would overwrite other values beyond the string. So let's say a hacker has a function that is that does something malicious, like, I don't know, it steals your files and sends them to a remote server, and they know the address of it. So, I don't know, void hack. And I don't know, maybe let's say it's at address 0x0020? Oh, that's a horrible 20. The exact address doesn't matter. A malicious actor can say, my name is Zoe, another E, 0x20, and it would write I'm going to use that long form, the silly. And just to clarify, the program we wrote is immune to all that because fgets specifies the number of characters that it'll read at any one time. But make the very reasonable assumption that we're slightly worse at programming at that and let this happen. The malicious actor can say, my name is Zoe0x20, which is possible because chars are just numbers, and they could probably figure out a char with that exact value. They would overwrite the return address, and then when the function returns, it would suddenly be in void hack. I once did this accidentally. I was working on a project for the university's WebLC3 simulator, and there's a test program that badly managed the runtime stack, and one of the test cases ended up overwriting the return address, and it just went somewhere in the heap and started interpreting whatever as code. And it was pretty difficult to diagnose the issue because the transition from regular program code to absolute garbage happened at the return statement of a function, whereas the corruption of the return address happened far earlier. So this stuff sometimes happens in the real world. Real-ish world, as real as it gets when you're writing software for universities to teach stuff with. One more thing I want to explain with the runtime stack is that each function has its own stack frame. So this is all a stack frame for our main function. But then you could also imagine that our main function calls other functions. Let's say we were doing this string example from last class, and you had a function to copy a string and a function to compare a string. If for some dumb reason, this might not be so dumb, if copy called compare, let's say, for a weird example, if it wanted to verify that it copied the string's contents correctly, then the runtime stack would look like main at the bottom, copy, and then compare at the top. And as functions are called, stack frames are pushed and pop off the stack. So when compare returns, copy will be newly at the top of the stack. And then if copy calls some other function, that function's stack frame will go to the top. Excuse me. And that's sort of the secret to automatic memory management. The compiler or the operating system, probably a bit of both, understands what we mean by calling functions and returning from them. So it's able to recognize a return statement and pop all of the function's data off the stack. Pretty easy, or not easy, straightforward. It's pretty convenient. In later classes, we're going to talk about the heap and pointers and dynamic memory management, and it's going to kind of suck, but it'll teach you so much about how computers really work and make you a better programmer in the process. One more tidbit is that the stack has limited space allocated to it, and I would hope that in a real computer the stack can handle more than 3 stack frames, but this is a kind of sort of accurate picture of something that could actually happen. If you call so many functions that it exhausts the space available on the stack, then you'll get an error with a message that you probably heard in another context before. That's called a Stack Overflow. Yeah, and the logo of stackoverflow.com even depicts a stack tumbling down, perhaps to depict a Stack Overflow error. Honestly, I think null reference would have been a funnier name for the website, but I don't know, I don't make websites. So that's all for the stack frame thing example. I think I'm going to leave this on the projector so that anyone who wanted to copy bits of it and wasn't able to do so can do so. But the lecture's basically over. We talked about the stack, drew a picture of it, and next class we're going to use this knowledge of the stack to explain why we can't return arrays and find a workaround to do so. So yeah, that's it. Here's the diagram. Come up to me after class if you have any questions, and apart from that, have a great day.